So to understand Einstein's axiom of general relativity, we need to go a step further here. Now, when you're standing on the Earth, we know which way is down because that is the direction gravity is pulling us. We feel a force downward. Well, if we replace mass here with inertia, then Newton's second law here still holds, even under relativity. We just have to recognize that mass, which Newton proposed was inertia, is only part of the inertia. And we have to increase the inertia as the velocity of a body increases. So the relativistic inertia, which probably doesn't surprise you, is transformed with the same square root of 1 minus v over c squared. So as the speed of the object goes to infinity, or gets closer to the speed of light, the inertia gets closer and closer to infinity. This is another reason that the speed of light ends up as a speed limit for the entire universe. Because remember, inertia is your resistance to changes in speed. If your inertia becomes infinite, well, you're not going to change your speed, are you? But Einstein was the one who realized that if you take someone and you put them in an elevator, you close the doors and you make this an elevator with no windows, no gates. It's an elevator that you cannot see out of. We've all ridden in elevators before. We know that when the elevator goes up, we feel heavier because there's a force pushing up on us from the floor. When the elevator goes down, we feel a bit lighter because we are starting to accelerate with that elevator. Einstein's realization was that when you're standing in a sealed box, you cannot tell the difference between having a box on a planet with a certain amount of gravity or having that same box out in space with a rocket on the bottom that produces the same acceleration. If you are trapped in that box, you have absolutely no way of distinguishing which of these two situations you are in. And that concept is what unlocked the key to incorporate acceleration into the special theory of relativity and turn it into the general theory. Because with an accelerated reference frame, now you can deal with planets, and now you can deal with gravity. And this is where relativity finally started to be massively adopted. For the first 10 years, it was an uphill battle getting anyone to even consider that it was correct. But some of the predictions of the general theory of relativity were easily testable. And, well, we'll see exactly how that turns out in the next video.